And we are live. Welcome to the 30th Astronomy on Tap. Woo.
Welcome, everyone.
I am MC Carbon Queen.
And I am the second MC, Blue Moon Skater Girl.
And we will be running the show for you tonight. So before we get started, MC Blue Moon Skater Girl, what are you drinking tonight?
I am drinking Moscato that I ordered 30 minutes ago. And I'm glad it got here in time. What are you drinking?
That's beautiful. I unfortunately have to drink coffee tonight because I'm working on a James Webb Space Telescope proposal that will hopefully get accepted. Yeah, fingers crossed. All right, so before, oh, sorry.
When is the proposal happening?
It's going to be due next Wednesday. We're doing great. Everything's great. Everything's fine. All right, so to get started, we have some announcements. So first, not that. Let's go all this way. All right, so we're still doing trivia. So anyone who's interested, go to this link, tx.ag/AoT trivia. Winners of the trivia will actually still be gaining a prize, just like we did back when we were in person and before times. So please, if you're interested at all in the trivia, it's really fun. You should go do it.
All right, and please like and subscribe to our YouTube channel. This is where we host our AOTs right now, our pandemic version of AOT. So please support us there and tell all your friends about it. This is, you can also get to our links using AOT, or I'm sorry, text.ag/AOT live.
And you can also follow us on social media to get all of these important information as well and all the other fun stuff that we're up to. You can follow us on Twitter at AOT_BCS. You can follow us on Facebook and Instagram at AoT BCS.
And another way to support us is by supporting the place that used to host us in person, and that's the Grand Stafford Theater here at College Station, Brian. So you can Venmo Jose-Quintana-20, and this would be a Stafford tip to support the bartenders that used to host us. So.
And you can also support us if you're interested. To do so, you can just donate online at one of the two Cash Apps, Venmo or Cash App, and use the name AoT BCS. And if you donate more than $15, you're eligible to get a t-shirt that looks like this, or what Blue Moon Skater Girl is wearing.
Okay, and our next event is December 16th. And if you don't want to remember that, just remember it's the third Wednesday of every month. So the next one's going to be December 16th. And again, in our social media, you can find all the information.
And finally, put your questions in the live chat on YouTube. Don't wait and forget what your questions are. We have moderators that will be looking at the chat during each talk. And so at the end of the talks, we'll be accumulating all those questions and going through them. So put them in as you have them and everything will be great. All right. So if you would, Blue Moon Skater Girl can introduce our first.
Okay, so our first speaker of the night is Paul Zivick. He is a postdoc at Texas A&M, and it's his first year here. So we're really excited to have you. Some boring facts about Paul. He grew, boring in quotation, he grew up in Virginia. He fenced on an amateur team in college, and he loves all Cleveland sports. So let's welcome Paul. Clap, clap, clap. And what are you drinking tonight, Paul?
I'm drinking Slivovitz. It's a Serbian brandy, more or less. So.
Sounds amazing.
And I see that your name is Cosmopolitan, and I think that's clever.
Yes, Cosmopolitan, yes. Well, excellent. Well, thank you for that introduction. Should I go ahead and share my screen and get the chat, get the talk underway? Okay. All right. So thank you for having me. I'm excited to be here. I guess I am technically in College Station, even if I don't get to be in a, out at a place in College Station. I'm excited to be at A&M. So tonight, I'm going to tell you a little bit about the Milky Way, kind of the history of how we've learned about the Milky Way and the galaxies that live nearby. Won't you be my neighbor? And with that, we'll get underway. Let's see, there we go. Okay, cool. So as with any neighborhood, we should probably start with the place that we live, which is the Milky Way. And let's start all the way back, right? As long as we've looked up at the night sky, you can see the Milky Way. If you're away from the city in a good dark place, you can see the Milky Way stretching across, dozens of degrees across the night sky. And so as a result, pretty much every culture in the world has come up with some mythology around the Milky Way. That on its own would be its own talk, but I do want to share one lovely example that I found because it also connects to my hobbies. In ancient Babylonia, the myth was that the Milky Way was formed from the tail of the goddess Tiamat after being slain by the god hero Marduk. Now, unfortunately, when I saw the name, I was very excited for a moment because anybody who plays D&D, you may recognize that name. Unfortunately, it's not that. It is this, though. A goddess who turned into a river serpent to take vengeance on the other gods who killed her husband. But that's just one of many myths, and I highly encourage people to go and find out more about some of the myths that people have told each other, stories they've told each other about the cosmos for millennia. But from a people thinking about it in a more modern astronomical sense, there are we'll walk through kind of the timeline, the history of rough ideas that people had. So we'll start in the 4th century BC with Aristotle, who thought of the Milky Way as being the ignition of the fiery exhalation of some stars, which were large, numerous, and close together. So, you know, the idea of stars was there, which is cool, but maybe not quite the full picture. In 10th century, we had a Persian astronomer. So, and these are just examples of quotes, you know, hundreds, probably thousands of people have looked up at the stars over the millennia that we've been doing it. So these are just some select quotes giving you an idea of kind of the general thoughts about the Milky Way as it evolved. So the Milky Way is a collection of countless fragments of the nature of nebulous stars. So we're still thinking about nebulous stars, and nebulous or nebula is going to be a word that comes up quite frequent, coming from the Greek word for cloud. So you're going to see that repeated often. A few centuries later, this had slightly evolved, where maybe we actually thought about it as tight clusters of stars, which account on their concentration and smallness seem to be cloudy patches. So now we're getting to the idea that maybe these cloudy things in the night sky aren't actually clouds, but are made of smaller, more discrete things. And in fact, a few centuries later, Galileo, with the telescope for the first time, was actually able to see that many of these cloudy patches did actually resolve into smaller clumps of stars, as this astronomer predicted. And of course, then we get to the 18th century, where now we're actually starting to think about what is the Milky Way as a whole? What is the larger structure of the Milky Way? And so one explanation for why it looked this way is that the Milky Way's appearance is due to an optical effect from our immersion in what locally approximates to a flat layer of stars. And so starting to get an idea of, you know, now we're starting to put ideas out there and actually explain it. At the same time, so kind of as Thomas Wright and other astronomers were thinking about what the Milky Way is, William Herschel, set out to try and map the Milky Way. So this is a very famous depiction, illustration of what Herschel thought the Milky Way was. In the center here, you have the sun, and he assumed that every star in the night sky that he could see was at the same brightness. You have to start somewhere, so that seems as good an assumption as any at that time. And so then if a star is fainter, that means it must be further away. And so as a result, everything looks like it's more or less equidistant from the sun, although you do start to see there's more of a disk than there is just kind of a large clump, even on the other side of the galactic plane, which you can see here. So this large dark stretch kind of going in towards the sun is actually, to go back the other way, yeah, so it's actually this dust lane here that sits in the middle of our Milky Way. That obscures, not that stars aren't there, but rather they're hidden by the dust in front of it. But Herschel didn't quite realize that, and so thought it was actually an absence of stars. Of course, in addition to the Milky Way, kind of at the same time, we were starting to catalog things that weren't the Milky Way, that clearly weren't stars, but were something else. And this is something that astronomers have done and continue to do for a very long time, is when we find something we don't know what it is, we just start cataloging it and then trying to organize it. So there are a few famous examples of this. So perhaps one of the earliest, and certainly one of the most famous, is the Messier catalog, which was published in 1774, that included 45 objects originally. You may actually recognize the name Messier, or you may have heard some objects referred to by their Messier name. So there's either famous globular clusters that on a good bright, or rather on a good dark night, are bright enough in the sky that you can see it with an amateur telescope. And then there's a certain galaxy, a certain M31, better known as Andromeda, that was the 31st object that Messier marked in this catalog. Interestingly, this catalog was actually compiled for the purpose of listing what objects weren't comets, because that was what Messier was most interested in. And so he wanted to make sure that, oh, there's something in the sky. Wait, I've already marked it. It's not a comet. It's not interesting to me. Little did he know. Over time, oh, and so this is actually the first page from his catalog when it was published. Over time, people eventually published more and more catalogs. So Herschel, so the same William Herschel from the diagram, eventually published the Catalog of Nebula and Clusters of Stars. His son, John Herschel, then updated it to the General Catalog of Nebula and Clusters of Stars. And then eventually we had, in 1888, a final publication. Well, not final because it continued to be updated, but the new General Catalog of Nebulae and Clusters of Stars, which gave rise to the moniker, the name from the objects NGC. So if you ever hear NGC, this is actually where it comes from the new General Catalog. And they compiled over 7,000 objects to discuss, to use and study in the Milky Way. So at this point, we had kind of started to come to a head, right? We had studied the Milky Way and we started to think maybe it's a disk. It looks like there are lots of stars here. There's some kind of structure to it. And then there are these other smaller objects that seem to be embedded inside of it, question mark. Interestingly, during the 18th century, one idea that was proposed, most prominently by the philosopher Immanuel Kant, was the idea of island universes, that maybe these objects in the night sky that we see, these cloudy objects, aren't actually part of the Milky Way, but are a universe unto themselves, an island universe. And so as the catalogs expanded and we found more of these objects, the debate began in the community. Is the Milky Way the entire universe and everything we see embedded within it? Or are there other island universes out there? What is the scale of the universe? Eventually, the community wanted to have an out-and-out debate about it. This debate eventually became known as the Great Debate. When was the Great Debate, you might ask? Well, it turns out this is actually the 100th anniversary of it, this year is, that occurred on Monday, April 26th, 1920, at the 1920 National Academy of Sciences annual meeting. And this is actually a picture of the schedule for said meeting. And you can see down there at the bottom, the debate, which at the time was simply called the discussion section, the scale of the universe, by two astronomers who'd be debating either side of this question. So on one side, everything is part of the Milky Way. On the other side, these nebulae are independent of the Milky Way. In the corner of everything is part of the Milky Way, we have one Harlow Shapley, who had fairly recently graduated with his PhD just a decade before, and was kind of on his way up through the field. And this is the man himself. His arguments were centered around the idea, kind of distance scales. Andromeda's relative size is actually a great one. So Andromeda, at this point, we had large enough telescopes, we could actually see it resolved into a disk. And it was interesting because we thought the Milky Way might be a disk. So the question was, well, if Andromeda is like the Milky Way and is as big as the Milky Way, in order for it to be as big as the Milky Way, but appear as small as it does in the night sky, that would imply that Andromeda had to be millions of light years away. And surely the universe can't be millions of light years big. That has to be too large, right? Well, on the other side, debating against him was one Heber Curtis. This is the man. A little bit further on in his career at the time. And he was actually arguing. So Andromeda, once again, played a very prominent role in his arguments. And he was actually arguing that it was the rate of nova in Andromeda. So small, bright flashes of light from various objects going off, getting brighter in Andromeda, that made it peculiar. Because if Andromeda was just part of the Milky Way and there was nothing else special about it, it just happened to be part of our galaxy, then you would think that if things randomly happened, then there's no reason that one part of the sky should have more of these events than any other part of the sky. And yet we kept seeing a lot of these events in Andromeda. And so shouldn't it be its own object? Well, we obviously know who the winner is now, but even at the time, the community agreed that Heber Curtis actually won the debate, although not necessarily the evidence that actually both sides presented was more or less correct, but it was rather the conclusions that were drawn from the more or less correct evidence that the community ended up favoring Curtis. Interestingly, some discussion says that one of the reasons Curtis was favored is that Shapley didn't give exactly a great discussion of it. That at the time he was applying for the job of director of the Harvard College Observatory, whose board members were actually at this discussion. And so he was trying to give a very broad general lecture that might reveal his aptitude for being the director of an observatory. And so perhaps he was a little distracted from the science and more focused on his career. And so Curtis was able to give the more compelling argument that eventually one Edwin Hubble eventually found classical Cepheids in Andromeda, which allow us to measure the distance precisely to different objects, and did in fact confirm that Andromeda is millions of light years away. And so it must be its own object, and that it turns out the universe is much bigger than any of us thought. So at this point then, we now know, we've agreed as a field that island universes exist, that there is more out there than just the Milky Way. Andromeda obviously is a neighbor that is very like us, but is pretty big, all things considered. So what are some other objects that might be closer, but we've now realized are actually their own objects? Well, two come to mind, and these are two of the brightest objects near the Milky Way. The Large Magellanic Cloud and the Small Magellanic Cloud, one of which is one of my personal research focuses, and so it has a special place in my heart. As a quick aside about the Magellanic Cloud, I'm sure many people recognize the namesake for who they're referencing, Magellan, the explorer. But as a small aside about these clouds, so one, they are so bright that in the southern hemisphere, so northern hemisphere, we might not think about them as much, but in the southern hemisphere, they're so bright that on a dark night, you can actually see these by eye. And as a result, similar to the Milky Way for everybody, they have a place in pretty much every Southern culture's mythology. There are stories about these objects. And in fact, Magellan wasn't even the first Westerner, or the first Northern Hemisphere, I should say, to write about them. There were actually Persian astronomers in the 10th century who were already writing about the clouds. In fact, Magellan wasn't even the first European to write about these objects. About 30 years before Magellan, there were a pair of Portuguese sailors who actually saw the clouds on a on a trip south of the equator and wrote about them. Unfortunately, or maybe not unfortunately, depending on who you are, but as history goes, they eventually became known as the Magellanic Clouds. So just a small aside about kind of those objects, only because they have such a special place in my heart. However, in addition to these two objects, it wouldn't be long before a new neighbor moved in, or rather we found that a new neighbor was already living nearby. In 1938, Harlow Shapley, yes, the same Harlow Shapley who was debating the other side of the Great Debate, published in the Harvard College Observatory, surprise, surprise, he did get the director position, Bulletin 908, a stellar system of a new type. And this is one of the figures from his bulletin. So at the time, to do observations, all the observations were on photographic plates. And so people actually sit down and by hand count the number of stars and where they appeared on these plates. And so this is a reproduction of one such drawing, of one such plate, centered here. And so you can see, 15 stars, 16 stars, kind of teens of stars. But then all of a sudden, as you get closer to the center of the plate, suddenly it starts increasing and increasing. You get to hundreds of stars. And they realized that this is actually a separate object. This is a new object that had never been discovered before. We had seen globular clusters. We had seen the faraway nebula that we eventually came to realize are other galaxies like Andromeda. But Shapley made a few assumptions. One key assumption, so he made an assumption about the absolute magnitude of the brightest star. Didn't catch that error before, the brightest star. And he offered a few interpretations based on this. The assumptions present the sculptor cluster, as it was called, as a supercluster of the globular type and of galactic dimensions, or a symmetrical Magellanic cloud devoid of its characteristic bright stars, clusters, and luminous diffuse nebulosity, or a nearby spheroidal galaxy, highly resolved and of abnormally low surface brightness. These are all a lot of different words, and probably to non-astronomers may not mean much put together, and even to astronomers, this is kind of throwing every possible object it could be into a blender and saying, well, it's something. But eventually we realized that this was the sculptor dwarf spheroidal galaxy and represented the faintest galaxy that we had ever discovered. And this is actually, so then this is a modern picture of it taken with a 4-meter class telescope, a little bit bigger than the telescopes they got to use back then. And so you can see just how, if you weren't looking for it, and this is very, very resolved, but this is an object that could just hide among the other stars, given how low its brightness was. So this was in 1937 when the original observation was made, eventually published in 1938. And over the next 60 years, we eventually discovered 8 more objects, all like Sculptor, that were faint and took a lot of effort to actually find using these photographic plates rather. Eventually, it came to an end. Sagittarius, which was hiding on the other side of the Milky Way disk, was the last dwarf galaxy that we discovered using photographic plates, because we entered into the digital age. Photographic plates were quickly pushed out of the field of astronomy by the advent of CCD cameras. Actually, it's funny, there were still a few observatories using photographic plates into the early 1990s. And it was actually the astronomy demand for photographic plates that kept many of these businesses still making plates. The only reason they would make plates is for astronomers. So we kept a few branches of businesses afloat that would have otherwise failed much earlier. And with the CCD cameras, you had actually the first 2 major imaging surveys that began in the late 1990s with the 2-micron all-sky survey, now known as 2MASS, and the Sloan Digital Sky Survey, which would become known, I would say, as one of the most, as one of the best and earliest examples of these all-sky surveys. So this is this is actually a picture of the survey telescope itself out at the Apache Point Observatory in New Mexico. And what was special and what the CCDs allowed us to do is, with the photographic plate, you put it on the telescope and you observe up to a certain point, but then you have to take that plate off, because if you don't take it off, you're going to overexpose the plate and then you'll ruin your data. But with CCDs, you can continuously read out the data that the CCD has gathered. And so if you wait long enough and just keep a telescope point at the sky, as you read off the data, you can just watch the whole night sky drift by. And this is actually a technique that came to be known as drift scanning. And so rather than just having to do only a few spots over the course of the night, they could actually observe the entire night sky night after night after night and compile thousands of square degrees of observations, a scale that really had never been seen before in astronomy. And with this new unprecedented amount of data, we began to discover galaxies again, dwarf galaxies. The first one that was discovered was in 2005, the Ursa Major 1 dwarf. Originally, it was just the Ursa Major dwarf, and then we realized about a year later that there's actually another dwarf hiding nearby, and that is Ursa Major 2. And it became the faintest galaxy ever detected up until that point. To give you an idea of when I say faint, like how faint are we talking? Sculptor was 600 times fainter than the Magellanic Clouds, which is part of why it was so challenging to find in the first place using photographic plates. Ursa Major 1 is 250 times fainter than Sculptor, which would make it 150,000 times fainter than the Magellanic Clouds. This is a very faint object. To give you an idea of how faint this object is, so Sextans, which is another dwarf galaxy, is on the right, much brighter. And these are basically a plot of the stars in the galaxies, using some astronomical knowledge to make some selections about stars that should belong to this galaxy. And so you see what we would think of as a bright galaxy, bright dwarf spheroidal on the right. And then you have on the left, Ursa Major 1. Very few stars. And if I didn't know that there was a galaxy sitting there, you could tell me that that was a random patch of sky, and I might believe you. That's how faint these objects are. And as a result, these would eventually become known as the ultra-faint dwarf galaxies. And over the next 5 years, using SDSS data, we would discover 15 more of these, ending with Pisces 2 being the last SDSS dwarf discovered in 2010. Now, another problem we actually had, and this brought the total known Milky Way satellites up to 27. So we went from 2 to 10, now to 20, or 2 to 11, and now to 27. But there was a problem with SDSS. I mentioned it was in New Mexico, which means it can only really observe the northern hemisphere, a little bit into the southern hemisphere, but by and large, we're missing half the sky. And so who knew how many galaxies there were still left out there to discover? But new surveys were on the way. In 2013, the Dark Energy Survey began. So this was a revolutionary survey. To give you an idea of the instrument that was used for this, the Dark Energy camera consisted of 74 CCDs for a grand total of 570 megapixel detector, which, if we want to put it in modern terms, would be 47 iPhone 12 cameras all stacked together. And indeed, when you actually take a look at what the detector looks like, the detector, to give you a rough idea, is probably about the size of a human torso, not to be macabre about it. And you can see it does almost look like somebody took a bunch of iPhones and just stuck them on the back of it. Obviously, those are actually the CCDs themselves. But it is a very large camera that can see multiple square degrees at a single shot. To give you a rough idea of how big that is, at least compared to other telescopes we have, Hubble only sees a few square arc minutes in a single field. And so this is thousands of times larger than that. Yes, yeah. Yes, and then as with SDSS, with the first data release of this, deeper photometry than we'd ever done from the ground, 9 new ultrafaint satellites were discovered within weeks of the data being published. Over the next 5 years, so between then and now, between DES and other ongoing survey efforts around the globe, we've discovered 36 new Milky Way satellite candidates. I do say satellite candidates as they're getting small enough and faint enough that now we're getting back to our original cataloging issue, our original nebula issue, where we called everything a nebula because we didn't know what it was. And now we're getting to a point where we're discovering things that maybe are star clusters, maybe are galaxies. And we're starting to really ask deep questions about what does it mean to be a star cluster and what does it mean to be a galaxy? To give you just a nice picture here, the 11 classicals are in blue, the 16 SDSS dwarfs are in red, and all of the galaxies discovered since, or all the candidates discovered since, are in green. Just as a quick timeline, I think I'm running pretty close to my time. 1920, we had 2, and then 11, and then 27. And now we have more than 60, thanks to a vast number of surveys. DES, Pan-STARRS, SMASH, HSC, and many, many others, and many more on the way. And so I'll go ahead and leave my summary up here. 100 years ago, we were debating whether or not the Milky Way was the extent of the universe. Today, we know more about our local neighborhood than ever before, thanks to cutting-edge technology and innovation. And in turn, we can start to use this to learn more about the broader universe around us. So thank you for your attention, and I'm curious to see what questions we have. Let's see, okay, cool. So we have some questions here. Or should I read the questions? Do I let the MC read the questions?
We can
take care.
Okay, cool.
Thank you so much. That was amazing. Like incredible history facts that I had never heard about. So thank you. So do you want to ask the first question, Arvin Queen?
Sure. So the first question is from this person named John Cohn, whoever he is. But have there been many false detections of faint dwarf galaxies, since they can have so few confirmed stars?
So I wouldn't say many. We've only just kind of gotten into the regime where we have telescopes and surveys sensitive enough to find these kind of borderline objects. There was one actually that we thought was discovered in DES data. Follow-up observations revealed that it wasn't. That was actually led by a graduate student here at Texas A&M, Sarah Cantu, who published. It's one of the cases where a null result was actually a very interesting result because it turned something we thought was there into actually it's just noise that. The universe is a messy, random place, and sometimes stars happen to align together, and it looks like something, but maybe it isn't actually something. So it's not rare, it's not common, but it does happen.
Right. Thank you. And so we have another question from Matthew Priel. Do you have any thoughts on a modern great debate that could occur now? And what do you think we might not have figured out as we think we do?
Ooh, a modern great debate. I mean, the one, if we're framing it as a great debate where there are two sides to it, I think the one thing that comes to mind is the Hubble constant, so the rate of expansion of the universe, which, depending on where you're measuring it from, what tracer you're using, astronomers are there are two different values that people seem to be centering around. And so there's kind of a debate as to which one you should believe. It could be that, similar to then, the evidence is right, but our conclusions are wrong. One value tends to be drawn from tracers earlier in the universe. The other tends to be drawn from later in the universe. So maybe there's something actually happening, something evolves that causes us to mismeasure it at different points in the universe. And so maybe everything is still kosher, is still coherent with each other, but in a way that we don't quite understand yet. I'm trying to think, what was the other half of the question? Great debate, or, something we think we know but might not. I mean, dark matter has to be the obvious question. We think we don't even think we know what it is, but we think we have an idea of what it is. But there are still I'm sure there are plenty of unexpected things that it could end up being. So for me, those are kind of the two that come to mind. But it's also a broad enough field. There's so much research being done that I'm sure you could ask a different astronomer and get a completely different set of answers.
There's a lot that is in the debate, but yeah, those are two very important things.
All right, the next question we have is from Cosmic Kid. So why do the CCDs in the DS image look like they're different shades of blue in that one photo that you showed us?
Yeah, that's a great question that I don't know the answer to.
That's fine.
Yeah, I am not an instrumentalist. I don't build the telescopes. I just use them very gratefully. But no, I don't have a good answer for why that is. So.
And that's totally fine. Thank you. I think we have one more question.
Okay, so from Cosmic String, what is the largest galaxy discovered so far?
Ooh, largest galaxy discovered so far. Let's see. I don't actually know. So the largest galaxy discovered so far is probably going to be at a slightly higher. So it's probably, right, so light is weird. Light and time are kind of interchanged. And so when we look further out in the universe, right, light can only travel so quickly. So when we look further out in the universe, we're actually looking back in time. And so my research tends to focus on the very close by, that's more or less right now. The answer to your question, I suspect, lies slightly further out into the universe, slightly further back in time, where you had a lot of big galaxy mergers happening. So we think the universe is kind of this web-like structure, that you have dark matter running everywhere, and the normal matter, or light matter, sits on top of the web. And you eventually get stuff drawn into the vertices of the web. And so as you get more and more matter piling on there, you get bigger and bigger galaxies. And so I'm sure there's probably some central web, conjunction somewhere nearby, maybe a billion or 2 billion light years away that I'm not familiar with because I don't study that, but that has that is significantly larger than Milky Way, 10 to 100 times larger than the Milky Way.
That's a great answer. Thank you. All right, that's all the questions we have. Thank you so much again, Cosmopolitan.
Thanks for having me. I really enjoyed it. So, all right, bye everyone.
All right, so next up we have, What's Up by the Cosmic Kid. Come on, Cosmic Kid. Hello, Cosmic Kid. What are you drinking tonight?
Oh, tonight I am drinking a very lovely cold brew infused Jameson, which is
sounds delicious.
Delicious.
Well, we'll take it away.
Thank you very much. All right, so welcome to What's Up, the monthly show where I talk about what's up in the sky that you can observe either with your naked eye or if you have access to some binoculars or a small telescope. There's a lot of stuff you can view that's pretty awesome. So first off, I want to talk about Pleiades. I saw this just the other night. It was really beautiful. It's also known as the Seven Sisters or Messier 45. You've heard from Paul earlier what the Messier objects are. It's also known as Subaru in Japan, which is actually where the name of the Subaru car company and their logo comes from. It's from this asterism, as it's known as. It's easily visible with the naked eye, And it's beautiful to look at. You can see all the really, really bright stars pretty easily with just your naked eye. It's part of Taurus, so if you want to find it, you basically have to look east around 9 p.m. And it's pretty easy to find and pretty obvious to find. One interesting thing about the Pleiades is actually that it's such a large cluster relative to us that you can't actually fit all of it inside of a telescope. With maybe some sizes of binoculars, you can see all of it. For the most part, the best way to view all of it is just with your naked eye. Next up, I want to talk about Orion, which is one of my personal favorite constellations, and it's one of the most famous constellations in the world. You want to look just under Taurus around 9 p.m. If you can wait a little bit longer, it's probably better, although it's pretty nice that they're both right next to each other, so you can see both of these in the same night. And one thing you want to check out is the Orion Nebula with a binoculars or a telescope. So if you look at this image of Orion, you've got Betelgeuse, the famous red giant at the very top that everyone thought was going to go supernova, but maybe it's not actually. Who knows what's going on with it? There's a lot of other famous stars. If you look at the 3 stars make up Orion's belt and kind of go down a bit, there's a couple of brighter spots that's known as Orion's sword. It's also Orion's Nebula, which is absolutely beautiful to see with binoculars or a telescope. And even if you live in a big city, you could see it pretty easily, even from a big city with all that sky pollution, skylights, you can still see it. So it's a really wonderful, wonderful thing to look at. The last thing I want to talk about for this month is the Leonid meteor shower. So this is coming from the comet Tempel-Tuttle. It's visible throughout the week. The peak was actually last night, and it's best observed around 3 a.m., but you can probably see the meteors throughout the night. It's not super active this year, but I was lucky to catch a glimpse of a few meteors when I was out observing just a few nights ago. So who knows, you might be lucky. I recommend packing a blanket and maybe packing some tunes and you can just spend the night staring up at the sky. I hope you see some meteors. And that, my friends, is what's up.
Thank you. I actually see the Pleiades every single night because I take my dog out on a walk, and like you said, it's really easy to spot. So
Absolutely.
Not to be confused with the bigger Little Dipper. That has been something that people have asked me about.
Yeah, no, those are at a completely different part of the sky.
Yeah, and also much smaller. Okay, so up next, we have the Dark Matter Dude telling us what's going on in astronomy today, and it's called In the News. So give it up for Dark Matter Dude.
What are you drinking tonight, Dark Matter Dude?
Hello. Yes, I'm drinking kind of a cranberry take on a margarita. It's one of the holiday drinks that my partner made.
Nice.
So, and it's got this fancy not umbrella thing.
That's beautiful.
Yeah. Okay. So let's see if I can get this going. Cool. What's up, space enthusiasts? We are going to talk about what happened in the news the past month, and we are going to start that now, maybe. Okay, cool. So the first thing, you may have seen a headline about an Earth-sized planet in the habitable zone. So we've talked about like exoplanet discovery here before. Just as a refresher for anybody that's new. There is a space satellite called TESS, which stands for the, transit. Oh no, I had it, then I lost it. I drank too much. Okay, we're good. It's fine. So TESS scans the night sky looking for transits. You can tell this is real. Scans the night sky looking for transits of bright stars, basically. So like all the brightest stars, TESS is basically scanning along the entire sky. I'm looking for transits. So that's when a planet is orbiting another star. It passes in front, blocks some of the light, kind of like what you see in the bottom right corner. So TESS found a planet, not surprising, but what is surprising are the properties. So it's about the same size as Earth, and it's actually in what we would call the habitable zone. So that's the range of radii of distances that you can get away from the sun or a star, where you could feasibly have the right temperature for liquid water to form. Basically, is the idea. So it's really interesting. So it's orbiting a red dwarf, which is a much fainter star than our sun, but it's orbiting way closer. It orbits its year is just over a month. It's 34 days. So those two actually cancel each other out, and you get an Earth-sized planet in the habitable zone, which is the first time that we've had that. Yeah, so small star orbiting really close, those things cancel, and it's getting about 86% of the light that we get from our sun. So it's about comparable. Now, very important, this does not mean that we found a planet that definitely has life, and it might not even mean a planet that probably has life. What we don't know are a lot of things. We don't know the planet's mass, we don't know its density, we don't know its chemical composition of its atmosphere. This could be like Venus, or something that could be extremely toxic to life or something like that. So we don't know a lot of these things. But what we do know, what we have found for the first time, is an Earth-sized planet in the habitable zone. So that's cool. OSIRIS-REx booped Bennu. So OSIRIS-REx is a satellite that we humans launched at a tiny asteroid. It's about 0.5 kilometers in size. And it's been orbiting this asteroid for about 2 years. And just recently, on October 20th, there was a very successful, what we call touch and go operation. So I'm going to hit play on this and maybe skip ahead a little bit. So this is live shot from the satellite, kind of going around this asteroid. And eventually it's going to stabilize. It picks where it's going to land. It's landing. And you can start seeing the arm sort of stretching out. Eventually, here we go. Yeah, so there's the arm stretching out, landing. And then there's like this explosion thing that happens. So what was going on there was this satellite basically landed and then had a very high pressure nitrogen blast to basically stir up all the rock that's on the surface. And then some of that blast was aimed so that smaller bits of rock would falling into a collecting area. And so it blasted, collected all this rock, and then launched back up towards home base. And so we successfully collected, asteroid material, and that's super cool. We hoped to collect about 60 grams. We may have gotten over a kilogram, which is a lot. It was actually so much that the satellite couldn't actually close the containment vessel properly, and so it was just leaking space stuff like this asteroid into space. And then on November 2nd, we successfully lost enough stuff in order to close the container. So now OSIRIS-REx is heading back to Earth so that we can study all that awesome asteroid material further. That's really cool. Okay, update on this Venus situation. So last month, maybe 2 months ago, you may have seen a headline about phosphine on Venus. The general idea was that phosphine is this chemical signature that we only know of biological ways that you can produce phosphine in the levels that allegedly were detected on the surface of Venus, on the upper atmosphere levels of Venus. So a lot of times in science, you get these really big, strong claims. They might be somewhat controversial. And, something that happens in science all the time is that like other teams of scientists will kind of do their own independent analyses, kind of check your work, make sure that everything stands to snuff, basically. So there were a whole bunch of these other articles that were kind of trying to throw some cold water on this idea. So first one looked at how exactly they were fitting the data. So you can kind of see this in the plot that's on the right. There's all this kind of noise, jitter up and down, and then there's this dip. That dip is the signal from that people thought was phosphine. And it turns out that if you kind of change the way that you fit that line to figure out how much phosphine there is in the atmosphere, if you do it different ways, you can get a less strong signal or a stronger signal. Most of the time, it's a less strong signal. So that's one way that this result was kind of clouded on. What was, okay, the way that you fit your data made it seem like there was more signal than there actually was. Then there was the stuff with the actual telescope data processing procedure. And so whenever you download data from telescope, there's a lot of data processing to turn what the telescope sees into like what humans and machines can work with. And a new data processing step, basically, if you work with that new upgraded data pipeline, the signal goes away, basically. And then another idea is, okay, let's assume that phosphine exists on Venus. There's not just this one area of light, a frequency of light that we can detect phosphine in. We can look in other frequencies. So a different team looked at a different wavelength frequency to try and find the same signal, and they found nothing. So all these three different big stories kind of cast some cold water on this. Now, the phosphine story isn't done. The original team looked at all these results, reanalyzed their data, including the new data processing pipeline, and they still claim, hey, we still detect phosphine. It's at a 7 times lower abundance, but they still detect, that's what they claim is that signature. So the story here is science is a multi-step process, and it takes a while for everybody in the scientific community to kind of get on board. We all have to do our own types of analyses to kind of figure out what's going on with a particular thing. The last one, this is the fun one. The moon is wet, kind of. So the idea here is that SOFIA, an infrared telescope with a 2.5 mirror, that is literally just, they took out the main entry doorway of a 747. They took that out, took out a lot of the guts of the 747 and put a telescope there. And so when you're observing the SOFIA, you can actually like fly on this airplane and like change things to basically get the data that you want. It's fascinating. The FAA was not a fan of blowing a hole in the airplane and putting a telescope pointing out of it. Just some fun stuff in astronomy. But basically, so a team of astronomers used SOFIA and pointed SOFIA at the moon to basically try and detect re-emitted sunlight that would be a signal of water. So basically, water molecules could absorb reflected sunlight, re-emit that sunlight, and then we would see this enhanced water vapor signal, water signal. And we actually do see that. SOFIA found it in 6 different spots, or several different spots, spread along kind of the center of the moon. We've known about water at the caps, but now this is more spread a little bit more evenly. And it's really cool how this got here. So the idea is that micrometeorites slam into the moon. There's ice and water on those meteorites, and the act of slamming into the moon basically traps the water molecules in glass, kind of. And so there's individual water molecules shielded in glass that are emitting the sunlight and putting out the signal. Important thing about SOFIA is that because it's a water line, in order to not detect the water, this is why SOFIA is so good for this. In order to not detect the water in the Earth's atmosphere, you need to be above the water in the Earth's atmosphere. And that's why SOFIA is up on a plane, basically, is to observe these wavelengths that would be blocked from the ground. Now, one kind of not great part is that NASA tried to tie this result to the Artemis program. And so without getting too big into the details, Artemis is basically a directorate from above the chain in government, above NASA's head, that basically said, hey, NASA, we want to go to the moon. We want you to land people on the moon, boots on the moon in 2024. There's a lot problems with that. But one problem is trying to use this. NASA made a big deal, and probably from the upper administration, to connect this result to Artemis, basically saying, hey, once we put boots on the moon, we'll be able to use this water to, hydrate, make fuel for our rocket ships, that type of thing. And you really can't do that, namely because, again, they're individual water molecules. It's not like there's like ice where it's several water molecules forming together into a lattice. It's individual water molecules encased in glass. So to say, oh, there's lots of water on the moon now, we can use this for Artemis, is wrong and possibly damaging. And it led to, so Twitter was really fun with this. And so it led to this line: NASA employee, oh, hey, you guys are back early. Astronaut, moon's wet. What? Getting into swimsuit and picking up pool noodle. Moon's wet. So yeah, that's it. That's my funny end. So yeah, that's it. That's what was in the news.
That was great. Thank you. We do have a quick question, actually, if Dark Matter Dude wants to stick around for a second. So you mentioned that the FAA was not a fan of putting a hole in a big plane and putting a telescope in it. Do you know how they were convinced it was okay, or did they just ignore their complaints?
Oh, I mean, they didn't ignore it, I imagine. I don't actually have, I don't know the story. There's probably people that I can ask for the story who aren't here.
Fair. I just thought you might know. That's fine.
No, yeah. I know.
Your friend.
I definitely know that it's not like the astronomy community went rogue and we're ignoring the FAA's orders and we put this plane in the air. That's not what happened. I don't know the exact story of how we convinced them that this was an okay thing to do. I'd love to know that though, and so now I'm gonna try to find that out.
Great, thank you. All right, thank you very much, Dark Matter Dude. All right, so our last speaker of the night is MCM33. So if you'd like to come on. All right, MCM33 is an amazing person. She's a very talented knitting maniac who in the before times could be seen knitting at our favorite whiskey bar, drinking a cool Hefeweizen. She once knitted a full-scale replica of herself that she occasionally puts in the passenger seat to get on the carpool-only lanes on highways. Very clever. And then finally, MC33 is one of the biggest fans of cats, and I can personally say that she is my cat's favorite aunt. MCM33, what are you drinking tonight?
I am drinking something called a Juicy Haze IPA, but I think the most important thing about it is it has a skeleton on it, which,
Perfect.
Testament to my Grinchy side. I'm still hanging on to that Halloween spirit. I haven't
support this.
into my heart yet, so here we are.
Well, take it away.
Thank you. All right. There we go. One day I will have Zoom figured out. It might take a while. All right. So as you can see, my talk is titled, Where's the Kaboom? There was supposed to be an Earth-shattering Kaboom, or the quieter deaths of stars. And if you haven't guessed by now, I really like the Looney Tunes. They were a very big part of my childhood. So once we started Astronomy on Tap in Bryan College Station, I suddenly remembered an iconic scene from Looney Tunes and decided that I had to give a talk whose title referenced that scene, no matter how badly I had to force it. And believe me, you will see that I really had to force it. So if you're not as familiar with Looney Tunes or you're kind of rusty on it, do not worry. The very first thing we are going to jump into is that iconic scene. And I'm going to turn on captions just in case. Oh, there, it's working. Brilliant. But yeah, just in case the sound isn't great. Oh, nope, that's not. There we go.
Pardon me again, Doc, but just what did you mean by that crack about the Earth being gone?
Oh, I'm going to blow it up. It obstructs my view of Venus.
It does? That's a shame.
Where's the kaboom? There was supposed to be an earth-shattering kaboom.
Gets me every time. So my justification for the title of this talk is that a kaboom is a supernova. And a supernova is one of the ways a star can end its life. It's this big, diffuse yellow-orange cloud here. Now, supernovae are one of the coolest things in astronomy. So what we have here is a before and after of a supernova. The arrow in this image is pointing to the star that went kaboom. And you can see that the resulting supernova is just so bright and so energetic. They're really cool. But they're often caused by really massive stars. So you might be saying, Tarini, yeah, supernovae are great. So what if they're caused by massive stars dying? Why should I care about how small stars die? And I say, yes, why should you care about how smaller, less massive stars die? Well, for one, a star very near and dear to us is, in the grand scheme of things, a small star, even if the sun doesn't look like that from the Earth. But aside from the sun being a smaller star in the grand scheme of things, in the universe, there are just way more stars that are not so massive than there are the really massive stars that, for instance, die in supernovae. Now, how do we know this? So to demonstrate this, I'm going to touch on something that's a little bit dense, but I believe in you. We will get through this. So one of the ways that we know that there are many more smaller, less massive stars in the universe than there are massive stars is through something called initial mass functions. So let's break that down. Initial generally means beginning. In this context, it refers to the time right after a group of stars has formed from a cloud of gas and dust. So initial, just after the stars have formed. Mass is just the mass of any star that formed out of this cloud. And function means it's an equation. There's math involved. There's lots of math involved in astronomy. This is just one of those times. So initial mass functions, at their heart, is usually an equation that looks like this. And what this equation is saying is the number of stars that have a certain mass, be that half the mass of the sun or half a solar mass, or 1 solar mass or 10 solar masses even, the number of stars that have a certain mass is proportional to that mass raised to some power. So the number of stars that have a mass of 7 solar masses is proportional to 7 solar masses raised to some power. Now the power itself is liable to change. It's set by observations. The short version is, from physics, we know that massive stars are really bright and less massive stars are dim. So if we looked at a group of stars, we could measure the brightness of that group of stars and use our knowledge that less massive stars are dim and more massive stars are bright. Combine that with the amount of light we're getting from that group of stars, and we can figure out what the power in our initial mass function should be. But the thing I want you to take away from this is the negative sign on that power. And if you'll recall from, I don't know when this is taught in schools, to be honest, but anyhow, negative power basically means that it's really 1 over the quantity raised to some power. So the number of stars with a certain mass is proportional to 1 over that mass raised to some power. And we know that if you divide 1 by an extremely large number, you get an extremely small number. And if you divide 1 by a not so large number, you get a small number, but it's not as small as a number you would get if you divided 1 by a really big number. So this is all to say, again, that there are just way more smaller, less massive stars than there are really massive stars. This figure, it's from Twitter, user Saidonahi at the top, you can see. It basically puts into a picture what I've been trying to say in words. The x-axis, y-axis is the number of stars basically, and the x-axis is the mass of stars. And yeah, there's a lot of information in this figure, but you will notice that this curve peaks at stars that have a mass of less than 1 solar mass. If you want to take a closer look at this figure in your off time outside of this talk, definitely would recommend it, because all these descriptions refer to what stages of life stars that began with, say, a mass of 10 solar masses or 100 solar masses, where they are now. So, but spoilers, so don't look too closely right now. So anyhow, you now know that there are way, way, way more less massive stars than there are massive stars. So we should think a little bit at least about how they die. But how do stars move through life in general? So stars, they do follow different tracks based on their initial masses, but they do all start off as balls of hydrogen, and they're really massive. I know I just said there are massive stars and less massive stars, but we're on the Earth. We can't really talk about mass. So stars are massive balls of hydrogen, and so their gravity causes them to collapse in on themselves. They start to contract as long as gravity can get away with it. But as gravity pulls the material of the star closer and closer into a smaller volume, it starts to get hot. And it gets so hot that the star can start to burn hydrogen in a process called nuclear fusion, which is basically hydrogen atoms get combined and turned into helium. And this process releases energy, which counteracts the effects of gravity and starts to push the star a little out against gravity. But it gets to a point where the energy being released by the burning of hydrogen just isn't enough to counteract gravity. So gravity starts winning again and collapsing the star. But then fusion comes back in and starts beating gravity in this fight. And that's basically the life of a star for a while. Gravity fighting with nuclear fusion. Though, for the sake of completeness, we will end up at something called degeneracy. I have included here for completeness. We'll get into it later. You can decide whether it's here for Looney Tunes completeness or science completeness. Anyhow, let's look at massive stars first, just to figure out how we even get to supernovae. So, for massive stars, a lot of burning happens, fusion happens in their core and the shells that result as they move through life. So massive stars start out with fusing hydrogen into helium in their cores, but eventually the hydrogen runs out. And then it starts burning in a shell around the core, and the core, which is mostly helium, starts burning into carbon. And then we go from carbon to neon, from neon to oxygen, from oxygen to silicon, from silicon to iron. And if you took a cross-section of the star at this point, you'd see it looks a little bit like an onion with different processes happening in different layers of the star. But the important thing here is that we have ended up on iron, which is not a good move for the star. And this is because in all the previous fusion reactions, hydrogen to helium, helium to carbon, carbon to neon, etc., etc., the star's been getting a pretty good return on its energy investment. It takes less energy to fuse hydrogen into helium than you get out of that process. So the star has been getting, and despite putting in energy to fuse these atoms, it's been getting out more than enough energy to counteract gravity. But iron is a turning point when it comes to elements. It's at this point that to fuse elements that are iron or heavier, you get out less energy than you put in. It's not a good investment. But the star is at this point. So to cut a long story short, gravity wins and we get a nice big kaboom. But we do usually have something left behind from the kaboom of a massive star. If the star is really massive, we can end up with a black hole, Or we can end up with a neutron star, which, as its name suggests, is made, I will hazard this and say, entirely of neutrons, if not mostly of neutrons. So that's what happens with massive stars. Let's move on to less massive stars, like the sun. So for smaller stars, we also begin with burning hydrogen into helium in the core, but eventually hydrogen runs out in the core, leaving only helium, though the hydrogen does continue to burn in a shell around our helium core. So we have our helium core, and unlike in massive stars, it's just kind of sitting there, not really doing anything. It's just not hot enough for helium fusion to happen. But despite that, gravity is still very much in play. And gravity causes the helium core to start to contract and get smaller and compress the material that's in the core. And here's where we come back to degeneracy. So degeneracy in astronomy and physics really basically means you've compressed something so much that you just cannot compress it further. Though, okay, yeah, you cannot compress it further. We'll leave it at that. Physics can get weird, but at this point, the helium core has been compressed so far down that it just can't be compressed any further. But temperature does rise. And eventually, we get to a point where the helium core ignites and helium fusion can now begin. So now our star is fusing helium into carbon and oxygen in its core, while hydrogen continues to fuse into helium in a shell around the star. And eventually the helium in the core does run out, and it also only starts burning in a shell around the core. So we have our core that's mostly carbon and oxygen, surrounded by shells of hydrogen continuing to burn into carbon and oxygen, and hydrogen continuing to burn into helium. A more scientific diagram that is way better than what I can make on Google Slides is here. It's basically what the star looks like at this point of its life. So we have our carbon oxygen core just kind of sitting there, surrounded by a burning shell of helium, surrounded by a blue helium layer, colors not true to life. And that helium layer is surrounded by a shell of burning hydrogen. And this whole thing is really small. I know it says it's not to scale, which means that this core here is way smaller. But anyhow, it's all surrounded by hydrogen. AGB just refers to the stage of the star's life. But what I want you to pay attention here is the radius of the star at this point of its life. This figure says it's 1 to 1.5 AU. AU stands for astronomical unit, and 1 astronomical unit is the distance between the Earth and the Sun. Now, the Sun is not a very massive star, which means it will go through this stage of its life billions of years from now. Don't worry. That's good for us because the Sun is almost certainly going to eat Mercury and Venus as it evolves. It could possibly eat the Earth, as you might have guessed. And this is a spoiler to say while all this has been going on, the hydrogen fusion and the helium fusion and that buildup of carbon and oxygen in the core, the star has been moving from fairly small, or smaller than it will be, and yellow, to large and red. That's because as the star evolves, its outer layers expand and cool off, and cooler things appear red. Conversely, hotter things appear blue. Just good rule of thumb. So now we have our nice big red star with hydrogen and helium burning in shells around a core of carbon and oxygen. And as simple as that picture sounds, a lot of complicated things can happen at this stage of a star's life. But the main takeaway is that all the processes that happen at this stage of a star's life cause stellar winds to develop. And these winds start to carry material away from the star. mass loss. Now, if we imagine that the material from the star is represented by Bugs Bunny, this is what happens as the star evolves. All the material starts to leave it, till we're just left with this lonely carbon-oxygen core. And we call this object a planetary nebula, even though there are no planets involved. The name is a holdover from 18th century astronomy. They were just sweeping the sky with their telescopes. Someone found this object. It was like, oh, that kind of looks like a planet. And everyone was like, yeah, it looks like a planet, but a little more diffuse. So yeah, we'll call it a planetary nebula. Okay. And we're stuck with calling these objects planetary nebulae. Now, as cute and surreal as my Bugs Bunny picture of the planetary nebula is, they're actually really beautiful objects. Just gorgeous. Like, look, this one is it's an infrared image of an object called the Elephant Trunk Nebula, probably due to the little trunk here. I honestly don't see where the astronomy names come from sometimes, but this is really pretty. And if I understood the NASA instructions correctly, the star that is at the heart of this nebula is this one, circled in red, right in the middle. And it just blows my mind that that seemingly tiny thing is what's causing this beautiful display. To indulge you and me a little more, here are more images of planetary nebulae. The purple parts of this image are X-ray emission, and everything else is optical emission. Optical roughly corresponds to the wavelengths that our eyes can see. And if you look at the X-ray emissions, I think that's where you can really see that the star is what is causing these lovely structures. To zoom in on one of them, the Cat's Eye Nebula, I got this in so many email forwards as the Eye of God, and I can see it. Anyhow, the Cat's Eye Nebula, really pretty, and you can see the source right in the middle there, a bright white object. And we call that object a white dwarf. It's the leftover carbon-oxygen core of the star that was just kind of sitting there, surrounded by the burning hydrogen and helium. It's not burning anything for fuel. The only way it can resist the influence of gravity is something called electron degeneracy. Now, degeneracy, we said before, it's like you compress it so far down that you just can't compress it anymore. Electron degeneracy basically means that it's the electrons that are saying, no, gravity, stop it. You're not going to push us around. We're holding this star up. Electron degeneracy. Now, since the white dwarf is not burning anything, all it can really do is cool off. And I think that brings us to something that's a little bit depressing, because since all a white dwarf can do is cool off, eventually it will become something called a black dwarf, where it doesn't emit anything that we can see. So in the very, 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 very distant future, the universe will likely just be a dark, dim place, because all the stars have gone through their lives. If the white dwarfs are just hanging out by themselves, all they can do is cool off. They will cool off completely at some point. So we're kind of lucky to be living in this era of the universe, as strange as that may sound. Fortunately, though, I did say very, very far in the future, white dwarfs take a very long time to cool off. In fact, if a white dwarf was born near the beginning of the universe, which is now about 14 billion years old, it will not have cooled off very much. Like, if it started at 20,000 Kelvin, it'll be just under that at the present. So kind of sad, but we don't have to worry about it. Now, you notice I did say a white dwarf by itself will cool off forever. And that is because, full disclosure, white dwarfs can go kaboom. It's a different kind of kaboom, and it's caused by white dwarfs that live next to a larger, younger companion star. White dwarfs are extremely massive, despite being about the size of the Earth. So they can pull material off of any star that is nearby. And if they pull enough material off, they can go kaboom. And this kind of kaboom is called a type 1a supernova. And you can see an example of one of those here. The bright white object that the arrow is pointing to is a type 1a supernova. And you can see that's about as bright as the galaxy that it is right next to. And galaxies consist of billions and billions of stars. So we've kind of come full circle, I suppose. Supernovae are really cool, but you should care about how smaller stars die. Anyhow, that's all, folks. Join me next time on a redux of Where's the Kaboom, where we will discuss whether Marvin's view of Venus was actually obstructed by the Earth, because I don't think that's true, but we should look into it. It might actually be true. All right.
All right, thank you, MCM33. That was a great talk.
And I loved all the references too.
Thank you for indulging me.
So we have a question, or the MCs have a question, and that is, what is your favorite Looney Tunes character?
Oh, character? Oh no.
I was assuming it'd be Bugs Bunny because you used all those references, but
Oh, I do like I've loved Bugs Bunny since I was a kid, but I think the older I get, the more I relate to Daffy Duck and just how frustrated he is about everything. I thought he was really annoying as a kid, but now like I get it, Daffy. I'm so like Bugs Bunny just keeps getting in your way for no good reason. I would be annoyed too.
good answer.
In fact, if I could plug a Looney Tunes episode, if you have not seen it, go watch Duck Amuck, which stars Daffy Duck, and basically has him at the whims of a very frustrating animator. It's immense. It's one of the most creative Looney Tunes episodes ever. Just watch it for the concept.
That's awesome. Thanks. So we have another question. This is from Cosmic Kid. So, the sun at some point in the future, the very distant future, but still in the future, the sun will start going through its aging process. And Cosmic Kid's question is, could we move to Mars or any more distant planets in our solar system and survive the big sun or the white dwarf sun? What do you think?
My money is not on Mars, but it's on a moon of Jupiter called Europa. Mars doesn't really have much of an atmosphere, and I think what little of its atmosphere is left will probably be stripped away when the sun goes through the later stages of its life. And Europa, one of the moons of Jupiter, it might have water or an ocean. So there was that really bad movie from the 90s where was it Waterworld? I don't know. But
I think it, yeah.
The world becomes covered with water and people live on big ships. We could maybe do that on Europa, but honestly, it's so far off. We should really invest our time in keeping the Earth safe. We'll figure it out. If we can keep the Earth safe to the point that we need to worry about the star getting to that stage of its life, we'll have figured it out.
It's a really good sentiment. I like it.
Right. It's going to be a long time before we're getting the effects of the expansion of the sun. So I agree.
All right. Well, I think that's it with our questions. So thank you so much, MCM33.
Thank you.
All right. And so this gets us to almost the end of our night. Let me make this bigger. All right. So we're going to run through the trivia answers now. So everyone who did the trivia, thank you so much. We're going to go through the answers so you can see who did successful and answered all the questions right. All right. So to get started, question 1. How many NASA astronauts have served the United States Senate as of the 116th Congress? 1, 3, 5, or 7? Well, the answer is 3. We have John Glenn, Harrison Schmitt, and Jake Garn, although we have a 4th incoming, Senator-elect Mark Kelly, who is also brother to Scott Kelly.
Question 2, how do astronauts vote while in space? I'm not going to go through all of these, but the answer is B, using a secure electronic absentee ballot sent through the Johnson Space Center.
Which also just happened this year, this particular image. All right, question 3. The majority of active American astronauts are registered to vote in which state? This might be unsurprising because this is where NASA headquarters is, but Texas. Yay.
And question 4, in 2019, NASA's budget made up what approximate percentage of the total United States government spending? 10%, 5%, 1%, or 0.5%. And you guessed it, 0.5.
Very tiny sliver. All right, question 5. Which costs the most? 1 night of observations on the Keck telescope, 1 night of observations on the Magellan telescope, paying an astronomy graduate student for 1 year, or buying your own 8-inch diameter telescope? It is definitely 1 night of observations on the Keck telescope, which is about $100,000 for a single night. The next would be the Magellan telescope, which is $50,000, and then $64,000 is the cost for paying an astronomy graduate student for a year. And honestly, in this opinion, it should be more. But...
All right, so which cost or is expected to cost the United States government the most? Building and launching a Kepler Space Telescope, Hubble Space Telescope, the James Webb Space Telescope, or air conditioning in the US military bases in Iraq and Afghanistan in 2011. And that is air conditioning.
All right, question 7. The most prestigious award in physics, the Nobel Prize, is named after Alfred Nobel, who made his fortune inventing and selling military explosives.
Question 8. As of 2020, how many women have won the Nobel Prize in physics out of a total of how many recipients? And that is 4 out of 215. And 2020, Andrea, guys, amazing. Love your representation.
Congratulations to her. How many women have served on the Nobel Committee for Physics, which nominates the people for the Nobel Prize in Physics? 4 out of 51. A little better than the people who've gotten it, but still very small.
And question 10, who put Galileo Galilei under house arrest and why? The Roman Inquisition, who found Galileo's heliocentric beliefs to contradict the church's teachings.
All right, and that ends our trivia answers. So congratulations to everyone who competed, and I hope that you got a really great answer from that. So we're going to move over to our announcements one more time. Let me get those open. All right, and share screen.
Okay, so just a reminder to like and subscribe to our YouTube channel, which is where we are hosting our AoT lives currently for the time being and in the future as well.
Then you can also follow us on our social medias. On Twitter, we are AoT_BCS, and on Facebook and Instagram, we are AoT BCS.
And to support the place that used to have our Astronomy on Tap in person, that is the Grand Stafford Theater, and that's Jose-Quintanas-20. And please support our bartenders that could just use the support.
You can also support us if you wish. You can donate online. We have both a Venmo and a Cash App account, which is called AoT BCS. If you donate more than $15, you are eligible to get an AoT t-shirt like the ones both of us MCs are wearing. They're very fancy. They also sport this design on the left-hand side. Very nice. Thank you, Blue Moon Skidoo.
Yeah. And our next event is December 16th, and that is the third Wednesday of every month. So don't miss it and keep learning about astronomy.
All right. So that is it for our announcements. And I think that's the end of the show.
Yeah, thank you to our speakers, to our hosts for In the News and for What's Up. And yeah.
All right, y'all have a wonderful night. We out.
Gig 'em.